Indeed, but I will be taking somehow the other direction than what we have heard in the morning. I will tell you about how physics can help machine learning rather than the other way around. So we are all here because of what happens kind of in deep learning that brought this empirical and engineering progress into many applications, including physics, and we have heard many nice examples of that. But there are also many, many things that we don't understand about deep learning. And here I give you a snapshot from an article that I have read a year ago or so, with what I think are three of the most important questions. So the first one, why don't heavily parameterized neural networks overfit the data? So that stems from the observation that, kind of naively in our first courses of statistics, we learned that if your polynomial has too high degree, then it overfits the data. It passes through every point and it doesn't extrapolate and generalize nicely anymore. But there is overwhelming evidence that neural networks do not suffer by overfitting like this. The more parameters you take, the easier the training gets and the better the generalization gets. And that's kind of a mystery. And you see that it's also related to some of the questions that we are often asking when we are applying machine learning to physics, such as how do we interpret our models? Because if it is true that it's much easier to train models that have way too many parameters, well, then it will be harder to kind of reduce the number of parameters to the absolute necessary that will then be easier to interpret. So these theoretical questions about deep learning are also deeply related to the questions that we are asking as physicists applying machine learning to physics. So the second question, what is the effective number of parameters? So this means what is kind of the complexity given the data set and given the network architecture, for instance, how many samples do we need of the data do we need to learn the task nicely? So this would translate directly, so having the right measure of complexity would not translate nicely to this sample complexity, but we just don't know of what this should really be. And obviously in physics and also in applications in biology, we sometimes have very few samples, so we would like to know whether deep learning actually is useful or not for that number of samples, and we have no idea. The third one about why doesn't backpropagation head for a poor local minima? So again, backpropagation is this gradient descent-based algorithm that is used all over deep learning. And for some reasons, it's walking in a non-convex, high-dimension landscape. And for some reasons, it ends up in minima that do generalize well, and not in the ones that do not generalize well and that we know by other means are there. So I would like to answer these questions. The really striking thing about these questions is that they actually come from the paper where they appear is 25 years old. So despite the immense progress that we have seen on the application side in these 25 years, on the theory side, many people are working on it, there have been progress, but by far not so impressive as on the application side. So we really need to advance on that. So where does the difficulty kind of comes from? So why is this so difficult? So the way I like to put it is that building the theory of something like deep learning really goes into subtle interplay of the three ingredients that I list here. The structure in the data on the one hand, the architecture and the algorithm. So let me just walk you through the three ingredients. Like for instance, what about the structure of the data? So we need to model the structure and the structure and correlations that are in the data. Why? Because if we didn't, we know from theoretical computer science that even very simple neural networks are NP complete to learn if we consider the worst case data. So we cannot be considering the worst case data because it would not be algorithmically tractable. But what we are doing in practice is algorithmically tractable. So there must be some particular property in the data that enables that. And we have no clue what that is. About the architecture, we kind of need to consider the multi-layer neural networks because of the overwhelming evidence that these are actually the ones performing so well. And on the algorithmic side, by that I want to say that when we are training neural networks, we have many parameters, the weights. And obviously, if the training algorithm is exponentially costly in the number of these weights, then this is useless. So we need to keep in mind that algorithmically, this is a tractable problem that is not even quadratic in the number of weights, but linear, or maybe we can add a log. And the kind of trouble with the traditional fields that are looking at this question is that they kind of nicely cluster roughly. This is, of course, very approximate. In these three directions, they are looking at one of the directions, and very few works actually make two of them interact, and almost none have the three of them interact. So this is where I would like to argue that actually physics is here maybe to help, because this system is kind of so complicated that we can look at it as a system in nature that we study with the methods for which physics was developed for thousands of years. So we would like to build a model of deep learning in which that kind of captures the salient behavior of the real systems and that we can understand better. And this is a direction in which kind of this direction of physics for machine learning is going. This is a model, this is a slide that is obvious for physicists, but just to say that in data science or say computer science, what we call model would be is something else than what we call model in physics. It's really the model, the form of the ansatz by which we are fitting the data. Okay, so that's not what we mean by models in physics mostly, right? The example of Ising model, it's not very realistic. It doesn't capture all the quantum mechanics of magnetism. It doesn't capture any details of any particular magnetic material. Yet it makes us understand what magnetism is about. So we are looking for something like that. So one natural idea of start thinking along these lines in machine learning is to look at this teacher-student model, which is a simplification of the real situation, where we imagine we have a teacher neural network in which we input random IID vectors, X, and then there are some ground truth values of the weights, W star, that produce the labels Y. And then the student network sees these examples of X and Y, as usually we do when we train neural networks. For simplicity, you can see the architecture of the ground truth network that can only make things simpler, so why not? But it doesn't see the ground truth values of the weights. And the question is, can it still recover the right function? Can it, from the examples, learn the right function? So that's a much simpler question. I put away all the complicated structure in the input data. Here I am just giving it IID vectors. So can we answer already this much simpler question? And answering this question actually goes back to physics works 30 years ago. So this model has been introduced in this work by Gardner and Derrida 30 years ago in the very simplest case where we don't even have hidden units. So it's just one layer neural network with no hidden units. But what's already non-trivial in this paper that they were looking at the high dimensional regime where the number of samples and the dimension are proportional. That means the dimension is very large. That means that everybody is far away from everybody, and all methods such as kernel methods and stuff that are based on kind of closeness are completely. All our intuition from low dimension is completely useless, and mathematically already such a simple case is challenging. And this model has been solved back then by what we call the replica method in physics of disordered systems, which is kind of a computational method that is not really mathematically well justified. So one thing that we did some 3 years ago, that we took the results of these sets of all the works. We prove rigorously that the results they obtained back then are actually the correct ones, so that our mathematical and computer science friends also accept them, and generalize to various cases. And the second point is that we also understood how is the optimal performance that we can be getting algorithmically achievable or not. So let me just show you one example here. For instance, the teacher generates the labels using a sign of the product of the data times the weights, and the weights are just Gaussian. In which case here, the red line, we are plotting the optimal achievable generalization error as a function of the number of samples divided by dimension. The red line is our theory, the black dots is the algorithm that we are here predicting matches the theory, and the blue squares is a result of logistic regression, which in this case is very close actually to the optimal, and it can be even optimized better and can be even closer. So if all the cases looked like this, then the kind of black box methods look as well as optimal, so this would be nice. But it's not always like that. One of the cases analyzed back then is you just need to change the weights of the teacher, make them plus minus 1. This should not change much, but actually it does. The optimal error becomes this red one. It has a phase transition. So here I'm showing you not machine learning for phase transitions, but phase transitions in machine learning, in this learning curve, in this high dimension limit. The algorithm actually has a gap. What we believe is the best algorithm has a gap. There is a region where it doesn't achieve a generalization error that it could. And the kind of black box algorithm is not picking any of this behavior. So we would like to understand that. But this very simple case, is it bringing us closer to the theory of deep learning? So let me be a bit critical with myself. So going back to my triangle, that I think is the key concept to keep in mind. What I described so far was an architecture with no hidden units, some message passing algorithms, not in the context of graph neural networks, but more in the context of graphical models, and IID inputs and teacher outputs. So I stripped away a lot of the structure that I would like to keep in. I would like to have here multiple, somewhat wide layers and analyze the gradient descent algorithms and have the right structure in the data. But now I go back to this concept of building and refining the model to capture the things that are not there yet. So I want to go around this circle a couple of times and include things and still have a solvable model. And after several circles, I will maybe be happy with what I end up with. So let's start here. Can I put in the hidden layers, the hidden units? So indeed I can, but only a few of them. So that's a model that is called the committee machine. We are still in this limit of high dimensional, high number of samples, and we consider we have order 1 hidden units. So that's a case that we can solve. It has been solved, non-rigorously 30 years ago. We kind of did a kind of modern look at that in this last year's NRS paper. And already in such a simple case where you just have a few hidden units, here I give you an example with just 2 hidden units. So that's the simplest possible, that 1 is like none. So already in such a simple model, we can exemplify things that we know from practice and from empirical experiments, such as the one that if you have just few samples, then the best method you can do is linear regression. And if you try deep learning, well, it's not doing better than linear regression. And as the number of samples is getting larger and larger, you can use more complicated networks, and they start learning functions that are different from what linear regression would learn. And this is known from practice, and this is known both as a function of the number of samples and also as the function of the training time, that these neural networks learn the simple functions first. So there's a series of recent works showing that. And this picture, I'm not going into details, but this model is exemplifying that. We have a sharp phase transition between number of samples below which linear regression is as good as any complicated model, and number of samples for which more complicated models can do better than linear regression. And so this is kind of putting us here. We can put in order 1 hidden units, and there are also some other works, if you know about those, that kind of go in that direction. But let me go to the lower side on the algorithms. So what can we understand about these gradient descent based algorithms? So one of the puzzles in empirical experimental studies of deep neural networks is that empirically the spurious local minima actually do exist. So there is a lot of theory works that are trying to show under which conditions in this loss landscape the spurious local minima don't exist, right? But then all those theoretical works are kind of superseded by a very strong set of experiments that are showing, well, but actually we are so overparameterized that there are even global minima giving us 0 loss error that actually do not generalize well. Yet the gradient descent based algorithms somehow magically manage to find the global minima that do generalize well, despite the existence of the other global minima that don't generalize well. So we really need to understand how the trajectory works and what really drives the dynamics of these algorithms and how regularizing them or treating them in different ways changes that. So we don't know the answer yet for very realistic models for neural networks, but we solved kind of this mystery for a simpler inference model that is this mixed matrix tensor model in paper that was last year in ICML, and extended version then in with more results version in NeurIPS. And the model is a one where the loss function is a sum of 2 terms. The x is some n-dimensional vector lying on a sphere. And here you take x times this transpose, and here you take tensorial product of these x's. So imagine P3, this is then a tensor. And you're minimizing this loss function with respect to x. And why the matrix and the tensor here are created from some ground truth x this way. And the goal is to be recovering the ground truth x in this high dimensional limit again here. So this inference problem is very high dimensional and goes to infinity and very non-convex. So it's really of the type of what we are kind of looking in deep learning. And here we actually manage, using the Couliandolo-Kurchan dynamical mean field theory, to compute the constant of the noise on the matrix and noise on the tensor, or the phase diagram, where the gradient flow finds a good minima. That means one correlating with the ground truth x start, and where it doesn't. So that's and that's that, like in a high dimensional non-convex problem. This I think is the first time that we kind of have down to the constant phase diagram of this. But then let's go back to this kind of popular explanation of why something like that happens. Right? The popular explanation is that as you increase the signal to noise ratio, there are these spurious local minima at different values of the loss, and then they disappear, and when there is only the last one, then you kind of find the signal because the gradient descent has no other choice than to go there. Okay, but this problem is so simple that we also actually have an access to completely characterize the number of minima at a given value of the loss function in this problem. And that's via a method that's called the Katz-Rice formula. So we do that in this model as well. And we end up with a different line in that same phase diagram, which is here this purple dashed line, that tells us that if we wanted no spurious minima to exist, it's only in this green region. Whereas in this gray region, the gradient descent still works, but spurious local minima do exist there. So here, this is an explicit example of this mystery that I was talking about that is observed in deep learning. But here we can really understand in detail where it comes from and what's actually happening. So here, from our analysis of the dynamics of the gradient flow, we actually find that the minima where it would be blocked are the ones at the highest value of the cost. And what decides whether it's truly blocked there or whether it actually finds the signal is the instability of those minima. So whether their Hessian has an unstable direction towards the solution or not. And this instability is something that we can analyze. And we actually end up with this middle region where we would have been blocked in these upper minimas, but they already became saddles, and they actually lead us to this blue one that interests us, that generalizes well. And so instead of focusing on this line where really there are no spurious ones, we should focus on this line. And when we do that, and when we do that, this is where we recover this blue line. Okay, so we have here really like explicit analysis of that. And I have just 2 minutes left, so I will not spend long time on this third side, where we actually are making steps into modeling not IID input data, but something more structured. So in particular, this is kind of the most recent work. So in particular, the type of input data that we can capture within the same type of kind of analytical tools where we can compute explicit phase diagrams of these learning problems is when the input data actually comes from something like generative adversarial network or variational autoencoder. So why do we want to do that? Because if we actually look at something like MNIST or SciFar, I mean, the one property we know about these datasets is that despite being quite high dimensional in the number of pixels, effectively the effective dimension is not so high. I mean, when we do some density estimations on them, people estimate the effective dimension of MNIST to something like 14 or between 10 and 20. And indeed, when we are training generative networks to generate something like these images, we know that we manage to generate GANs where the input dimension is very small. So with this in mind, this kind of motivates the model where the input dimension here, that would be the C matrix, the D is small. And then we are projecting it to higher dimension P, which would be the ambient dimension, and then kind of scrambling in by some nonlinearity so that it's not so easy to recover it just by, say, PCA or something like that. So that's a model for input data, and the labels, they come from this latent representation, so from the low dimensional manifold is the position on the low-dimensional manifold that decides the labels. And then the manifold is projected to high-dimensional and scrambled, and this is then what you observe and from which you learn. So that looks much more realistic. And fortunately also for us it's in a form that we can also solve in a closed form, both for the online stochastic gradient descent and for the batch learning. But I will not give you details on that, not today. I just end up with this phase diagram, with this diagram, where we are today in blue and where we would still like to get in green, and going around several more times. Hopefully we will end up with something like that more and more people will be happy as explanation of what's going on. And this is just a slide with the references that I covered in this paper. And then there's this review that came out recently that we wrote with a bunch of colleagues. That is mostly about the other direction of applying machine learning to physical sciences. So it's not up to date because there are so many papers coming in, but in March last year it was up to date up to our best knowledge. And I will open it for questions.
Thank you very much. Are there questions?
So thank you for the talk. I have actually one, maybe two, if no one else has another question. But can you go back to the graph where you show where you have the different minima and the CAC formula prediction?
This one?
This one, yeah. The color is the loss function or is just
No, the color is just the color.
Okay.
You have color in the different parts.
And if you plot the loss function, will you see more or less something like this? Since if you plot the loss function, do you have a big difference between the no spurious minima and the other region close to this?
So let me see if this is actually pointing. So here you will not have a big difference. It will be kind of smooth. But here at the line where the gradient flow starts to find in correlation with the ground truth, you will have a non-analyticity, and it will show up in the loss function.
Okay, thanks.
More questions? So in your kind of diagram of kind of the different aspects that you're approaching, when looking at the structured data, you only mentioned it briefly, you're kind of going from IID now to data that lies on a manifold that looks more realistic. Does it make sense to also think about going the other direction? How do we make the data so bizarre that deep learning no longer works? And is there a phase transition there in the structure of the data? Is that a question that one can ask, or does it not really fit in this framework?
Oh yeah. I think like that's probably a question that is answered in like a couple of works. Like because of the fact that in worst case data, the learning isn't complete. So there are works around where people construct examples where the learning is difficult, such as the parity machine. Like when you learn something that will be just you take IID vectors. And you take a teacher that is a neural network with, say, 100 hidden units, but then the output is the product of, say that the hidden units are signs, and the output is a product. So this is a nightmare function to learn, and deep learning will not learn it. It's not helping So we have examples of functions that are hard to learn, but they are bizarre functions. We kind of have to understand where is the boundary between what we actually are interested in. So that's harder.
More questions? If not, let's thank Lenka one more time.